Well, thank you so much. It's a privilege to be here, and I appreciate everybody for coming, and I appreciate the organizers for making this opportunity available. The talk, despite the title, the talk that I'm going to give today is follows this recent paper written together with Jaroslav Trinka, where we just derived a closed-form local integrand expression for all Twoloop amplitudes in planar n equals 4. And with this formula, besides being closed and compact and very simple, happened to be has some extremely nice properties. For example, it happens to make manifest the finiteness of all finite observables, such as ratio functions, for example. Now, this work followed on an earlier work written together, with Jaroslav Trinka and Simone Caron-Haute, where we described an enhancement of the traditional story of generalized unitarity at one loop to match field theory at the level of the integrand. So the outline of this the talk is going to start with one loop and motivate this, and then I'll derive the two-loop amplitude in the form that that Jaroslav and I eventually found. And we'll see some of the new ingredients, such as these elliptic contributions, along the way. Now, for better or for worse, for what it's worth, this talk probably could have been given 20 years ago. And in many ways, it won't depend, the results I'm going to describe don't depend in any way on any of the powerful technology developed in recent years, the recursion relations, the positive Grassmannian, the amplituhedron, or anything else. In fact, the only role played by those recent developments was to provide us with the computational strength required to verify the story I'm going to tell you. So when I tell you that something is true, it's because we've checked it by some concrete computation, and the two-loop expressions have been checked against BCFW recursion up to 14 particles, all 14 particle amplitudes. So although I guess this talk could have been understood 20 years ago, probably couldn't have been given 20 years ago. Okay, so I expect that most people here are familiar with the general framework of generalized unitarity. It's a very powerful approach to computing loop amplitudes, or at least as the way it's usually described. It's based on a very simple idea. Instead of adding up all the Feynman diagrams, the idea is just to choose an largely arbitrary but complete basis of L-loop Feynman integrals and determine the coefficients in this basis of any scattering amplitude as in terms of strictly lower loop data by cut conditions and matching all of the maximal cuts. And this is an advantage over the Feynman expansion because everything is determined in terms of strictly lower loop information. In principle, this approach to computing loop amplitudes is extremely clear and very straightforward, provided that you have two things: a complete basis of L-loop integrals and sufficient computer power to compute all their cuts and satisfy all the cut conditions to solve the linear algebra problem to determine all the coefficients. And in practice, you have neither of those. Even at two loops, the complete basis of two-loop integrals is not known, and the linear algebra required to find all these coefficients becomes absurdly difficult very quickly. I only point this out because I want to emphasize that what I'm doing here is not that traditional framework. There's no linear algebra here. What I'm going to do is write down the right answer. I'm going to just tell you the terms, and it won't involve a complete basis of integrals. In fact, it won't be a basis at all. We're just going to match field theory term by term, and we'll just find a nice expression. Okay. So let's start with a brief review of one loop, generalized unitarity. And just for the sake of time and simplicity, I'm only going to be talking about the leading terms. Of course, in general, the one loop, the story of one loop unitarity in 4 dimensions is to decompose amplitudes in terms of scalar boxes, triangles, bubbles, and rational terms. And so for the sake of this talk, I'm just, you can put dot plus dot dot dot. This is the leading term. So I'll be talking about just the leading term here. But I should say at the outset that this general story applies to all of the lower order terms and more general theories as well. Okay, so the basic idea, so this is some particular scattering amplitude we care about. We're going to decompose into a basis of standard Feynman integrals, which we can choose however we'd like, and a convenient choice, so boxes, triangles, bubbles, and tadpoles and rational terms if we'd like. Oops, I don't know why that. So these i's are just standard Feynman integrals. And by that, I just mean 4 Feynman propagators, completely ordinary. The only distinction is that I want to normalize this so that they have unit that the codimension 4 residues of this integral are unit in magnitude. That's the only extra bit of data. And then in terms of these integrals, the coefficients are very easy to compute, and they are given by what are now called on-shell diagrams, but traditionally maximal cuts or leading singularities. And the logic behind this is fairly straightforward. So to understand this, imagine instead of integrating the sum of Feynman diagrams on Minkowski space over the Feynman contour, imagine taking successive residues that put some sets of propagators on shell. So for example, if we did a little integral on a circle, putting all of these propagators on shell, we would isolate all the Feynman diagrams that have that propagator, and then we could take the residue, and we'd put that on shell. And taking 4 successive residues, so putting 4 Feynman propagators on shell, will result in just a rational function of the external data. By virtue of the fact that we're summing all Feynman diagrams of this topology, it's clear that all the corners are full tree amplitudes in this case. And they are evaluated at the internal momentum that solves these conditions that these 4 propagators go on shell. And these are just some point in loop momentum space, in complex loop momentum space, where these 4 propagators go on shell. And we know exactly what field theory has to be at that point, and it is given by this product of trees defined in in the normal way. The only bit of qualification that I want to add here, which might seem like a complication, but I think it's just critical to the whole story here, is that there is not one function with this topology, and solving these 4 quadratic equations does not correspond to a single point in loop momentum space. They always come in pairs. So there's actually 2 functions with this topology. One where so this is 4 simultaneous quadratic equations. It's not hard to see that there are 2 solutions. Well, there are many ways of seeing that there are 2 solutions. But the point is that there are 2, and they're not. And these 2 functions, the function evaluated on the quad cut 1, so on one particular point in loop momentum space, which solves these 4 equations, and then another one which is evaluated at another point in loop momentum space for the other solution. And importantly, F1 and F2 are generally different from each other. These are not generally equal to each other as functions. Okay, that's critically important. So just to emphasize that, I'm going to kind of make the box expansion a little uglier and say that the ordinary way it's written is this box times the sum of these things. Another way of seeing that there are always 2 solutions to these equations is by the global residue theorem. So this box integral has 4 Feynman propagators, and we know from the global residue theorem that the sum of all the residues is 0, so there can't just be 1. Okay, so if you put 4 propagators on shell, there have to be at least 2, and it's a little harder to see they're exactly 2. And that they have to be equal and opposite, and the residues have to be equal and opposite in magnitude. So this thing has equal and opposite residues, whereas field theory, the residue on one of the quad cuts and the other one are generally different. So this might seem a little paradoxical. So clearly, the right-hand side does not match field theory on all the cuts. The reason why this is justified is because these 2 points in loop momentum space, Q1 and Q2, for quad cut 1 and quad cut 2, are related by parity. And so this amounts to parity symmetrizing the answer. Said another way, it differs from the correct integral by a bunch of parity odd contributions. And that might seem like an advantage because you're saving yourself the effort of adding terms which integrate to 0, parity odd integrals. But I hope to convince you in this talk that this is not an advantage. This actually hurts you a lot. Okay. So for the rest of this talk, I'm basically not going to have anything to say about these on-shell diagrams. Excellent talks could be given and have been given about how these things are connected to Grassmannians and can be computed in beautiful ways, and they can be recursed and everything like that. In fact, for n equals 4, they're all computed they're labeled by permutations. But for the sake of this talk, I'm going to assume that everybody here just knows how to compute them or has a graduate student who can, and I'm going to focus more on the big picture. These are just functions that can be calculated canonically. Okay. So the advantages of this are fairly clear. So you just write down a basis, if you have a basis, and you just get to compute these Feynman integrals once, if you know how to compute them, which we don't necessarily know how to do at Twoloops either. Okay. And that's a big advantage. So if you look up in the appendices of many papers, you'll find the box integrals, the triangles, bubbles, everything like that, in some regularized form, and you can just look them up and tabulate them and refer to them later, and you can compute these things fairly easily in any quantum field theory in terms of this on-shell tree-level data, and that's important. The same thing applies to the triangles and bubbles, by the way, as well. Okay, but the disadvantages are many. For one thing, almost every single term in this expansion is infrared divergent, and so that they need to be regulated in some way. And unfortunately, the regularization procedures that we have, whether it's dimensional regularization or mass regularization, usually break the symmetries we know to be present in all of the finite observables that we actually care about. And so what we end up doing is that these integrals, which are tabulated in appendices, break all of the symmetries of the theory in some horrible way, so that when you actually combine expressions to find finite observables, it's a lot of work to see that they're actually symmetrical. So this need for regularization is one big disadvantage. And also, I think it's important that it actually does not match field theory, where we have a lot of good guidance from the recursion relations. Okay. So let me first describe how to improve this story. And it turns out to be a really small change that will allow us to match field theory exactly on every single cut, so we can remove this integration sign here. And so we get an integrand level version of the box expansion. Oh, one more little disadvantage here, which will come in handy later, is to point out that so this is going to be matching field theory at particular points, these Q1s and Q2s in loop momentum space. But it is just worth bearing in mind that not all of the codimension 4 residues of field theory are supported on these kinds of points. So if you look at the set of all codimension 4 residues in field theory, only some of them are these quad cuts. There are also a few others as well. And to see that this expression, the right-hand side, actually matches the other ones, which I'll show you in detail in just a moment, is actually a bit of work. Okay. So let's start. Now, for those of you who are very familiar with scattering amplitudes, I'm going to use some concrete examples. For the rest of you, just ignore the notation as much as you can. So in particular, to really emphasize the fact that these two things are not equal, that the residue on one quad cut and the other are not the same, there's an example. This is best illustrated in the case of the MHV amplitudes, which are maximally chiral. In fact, they're so chiral that they have no support on one of the quad cuts for all of the boxes. So every single box, one of the cuts vanishes, and the other one is some simple function. It's the tree amplitude, but that's besides the fact. I don't think I can restart. Yeah. Okay, so in the MHV amplitude, it doesn't matter which one, but one whole class of these cuts is 0, the residue in field theory is 0, and the other one is some finite answer. And so the box expansion gets this horribly wrong because the boxes all have support on Q1 and Q2, whereas field theory only has support on Q1. So this is the coefficient in field theory, and the coefficient on Q2 is just 0. Okay, just to illustrate this, so you can again ignore the notation here, but this is the coefficient, this is the particular box. And of course, because there are 4 propagators, the global residue theorem tells us that there have to be, the sum of all the residues is 0, so there are 2 different quad cuts, and they have equal and opposite magnitude, and so this just fails to match theory, field theory. It's just matching it in parity symmetrized form. The cure for this is to wonder how can we possibly modify this integral in a way that it matches the field theory on this quad on Q1, and it is 0 on Q2. Is there a way to chiralize this box so that it matches one cut or the other and not both, and in a way that doesn't introduce any other physical cuts? Well, because of the global residue theorem, in order to cut out one of these two support on one of these cuts, it's necessary to introduce another propagator. And if we want to make sure that we don't introduce any other physical cuts, so we want to match one cut at a time, we have to introduce a spurious propagator. And this can be done concretely in notation that I'm not going to explain very much by introducing basically another momentum, L minus x squared in the denominator, which is artificial, and then introducing a numerator designed exactly, completely fixed by the criteria that it's unit residue on Q1 and vanishes on Q2. So as soon as we've done this, this is completely fixed by that criteria, that we've added one new propagator and a numerator so that it matches field theory on one of the quad cuts and vanishes on the other. So now this chiralized box has support on only Q1 and not Q2, And of course, we can do this procedure for every one of these integrals and basically get a chiralized version of every box. So the question is does this is going to match the MHV amplitudes on all of these cuts, on all the Q1 cuts. And if we generalize this to all of the boxes, we get a proposal for the chiral version of the box expansion, where instead of, notice it has the same number of terms, by the way, where instead of having a scalar box, we have a chiral box designed exactly to match field theory on one physical cut and none others, and then another one for the other cuts. Okay, so this is guaranteed to match all of these cuts, but is it the right answer? And the answer is no, we're still missing something, and it's related to that small comment I made, that this is not the complete set of all of the codimension 4 residues of the field theory. But perhaps the easiest way, the most glaringly obvious way to see that this right-hand side could not possibly be correct is that every one of these chiralized boxes is finite. So the whole right-hand side, which matches field theory on all of these codimension 4 cuts, all these box-like cuts, can't be right because it's not divergent. We know that field theory actually has physically meaningful infrared divergences. So despite the fact that it's matching field theory on so much, it cannot possibly be the right answer. And the missing ingredient is related to this other set of codimension 4 residues, which are usually called composite leading singularities. But they correspond to cutting only 3 propagators, but cutting one of them twice. So this is very simple. If you have any 2 consecutive propagators that are separated by a massless leg, then when you set on the support of one of them going on shell, the other one factorizes. So remember, this is quadratic, and so when you set this to equal to 0, this propagator squared equal to 0, this one becomes a product of 2 things, and so you can cut it twice. So there are other codimension 4 singularities which correspond to points in loop momentum space where the loop momentum between the leg a minus 1 and a, this line right here, is actually 0. So not only is it on shell, but it's on shell and 0. So this is a soft collinear limit, and there are these extra n points where these triangle-like composite leading singularities need support, and it turns out we're missing all of them from here. It's kind of curious that they're related to soft collinear places. That's no accident. So in order to match field theory, we need to also include in this expression this leading singularity, which is just the tree amplitude. Of course, if we put no momentum through this line, this as an on-shell diagram is just the tree amplitude. So we need to add these integrals times the tree amplitude to match all of these cuts. And now, on the right-hand side, we have matched field theory on every single codimension 4 cut completely. In terms of these integrals that individually depend on some spurious x, that's a bit of a problem. But we've now matched every single cut, and it's a bit of a, you can show by the global residue theorem that the right-hand side is independent of x, and because of that, it has to be correct, and it is. So this is the chiral box expansion, and this correctly matches all of the cuts of field theory at the level of the integrand. For planar n equals 4, this gives exactly the right answer, that exactly reproduces the rational function that comes from the recursion relations. So we know that we've matched field theory everywhere. Very, very nice. And it has a kind of a surprising feature, which I wish I could have anticipated, but at this level it's kind of an accident, which is that because the divergences are universal, the sum of these triangles is the same for all amplitudes, and this coefficient here is just the tree amplitude. It means that all of the ratios of any pair of amplitudes with the same n, same multiplicity, is manifestly free of divergences. In particular, this renders all the one-loop ratio functions manifestly finite. So the ratio function is just at one loop is just defined as the one loop amplitude minus the one loop the tree amplitude minus the one loop of the MHV. Doesn't really matter. But the point is, if you put in this expansion, because the divergences are universal and always proportional to the tree, the divergences cancel out in this expression, and you get a manifestly finite term-by-term expression for the ratio functions. Now, what do I mean? What I mean by manifestly finite is that every single integral on the right-hand side can be evaluated without a regulator. Because you don't need a regulator to evaluate them, the right-hand side does not need to break any of the symmetries that you have of the theory, so this makes it extremely easy to write down manifestly dual conformally invariant expressions for all one-loop ratio functions, for example. Okay, now in a moment I'm going to use this as a bootstrap to kind of guess the structure for the two-loop amplitude, and I should say at the outset that this is a bit of a a morally incorrect way of deriving the two-loop amplitude, but it happens to be the way we did it historically. So I think at the end I'll summarize what I think is the more general and simple way of understanding the two-loop expression we found. But what I'm going to describe in the next couple slides is actually the way that we actually derived this. So basically, we were started with the idea that we wanted to make this property, this magical property that it broke into finite plus divergent parts, manifest. And if you do that, there's a unique form of the divergent part at any loop order. So you can always make this partition. This can just be operationally a definition of the finite part if you'd like. But if you have this, if the divergences exponentiate the way that we know they have to, in terms of finite lower loop amplitudes times the one loop divergence, this is just the sum of those triangles to some power, then it's a few lines of algebra to see that all ratio functions are expressed in terms of just finite quantities. And so we can use this as a guide to try to guess a form of the two loop amplitudes in terms of divergent plus finite. Again, this is the way we did it historically, not necessarily the best way to motivate it. But, okay, let's go with it. So if we want to make the two loop ratio functions manifestly finite, we want to put in this ansatz, that at two loops, the divergences are tree times one loop squared. This is the sum of the triangles. And the one loop divergence times the one loop finite, which is the triangle times these one loop finite boxes. Okay, as long as we have this as the ansatz, we're guaranteed we're going to get the all ratio functions finite. The only missing ingredient is really to make this multiplication a statement at the integrand level that makes it very, to upgrade this multiplication to an integrand level. And this can be done by, I keep hitting that button. This can be done by defining a merge operation, which can be motivated in a bunch of different ways, but let's just take it as a definition, that two x-dependent integrals, remember everything we have at one loop, so all the terms on the right-hand side depend on x. You can just take it, they both have x in the numerator and denominator, and just basically delete x. This introduces one new propagator. But it no longer depends on anything unphysical, by the way. There's no more unphysical propagators, no more x dependence. So, for example, this one loop, this triangle times triangle would start off like this, and diagrammatically, this triangle times triangle would turn into a double box like this. This, by the way, we know is right because the cut that cuts these things, the doubly composite cut, which cuts these 6 propagators and this one and that one twice, has to have the coefficient of the tree amplitude. And this merge operation preserves the cuts on both sides. For this term, we basically get triangle times box, and those integrals turn out to look like these pentaboxes and also double boxes, which I'll show you at the end. So the only thing that remains is to now see what these finite terms look like. And I'm going to tell the story the way it was historically, and I'll summarize it in a slightly different logic. Okay, so you're looking for all of now we're looking for just the finite contributions to two-loop amplitudes. And we know we're missing some of the cuts still. We have a lot of these divergent contributions. So let's just talk about all of the possible cuts of the amplitude that we're missing. One class of leading singularities of these codimension 8 points, these special points, are the so-called kissing boxes. They look like this. And it's natural to multiply this by just merging 2 boxes. This gives you a pentabox. This is guaranteed to match all of these cuts correctly. And if you just include these terms, you get all MHV amplitudes at 2 loops. For NMHV, you need another class of diagrams, which are these pentaboxes. First make an appearance for NMHV at 7 point. And you, again, merge box times box, well, triangle times box, and you get now all NMHV amplitudes. This was done about 5 or 6 years ago. Not in this form, but we had guessed these expressions. For n squared MHV, there's a new structure. We're missing some codimension 8 cuts, and it took us a little while to find it, maybe a year or so. Those are composite. Those correspond to double boxes, finite integrals again, but ones where you cut this internal propagator twice. Okay. Now, if you include these, you get all of these cuts correct, and you get all n squared MHV amplitudes. But as Marcus suggested in the last talk, starting at n cubed MHV, there'd be dragons, and something new has to happen. And it took us 2.5 years to figure out this extra little ingredient that first makes an appearance at 10 point n cubed MHV. Basically, the whole philosophy I've described so far takes points, isolated points in loop momentum space, these codimension 8 points, and matches field theory at each one of them. And the problem that happens in general at two loops starting at 10 point is that there are no longer well-defined special points to fix the amplitude. And the easiest way of seeing that this is just a big problem, and it's closely related to the appearance of elliptics, is to notice that the two-loop 10-point NMHV amplitude, n-cubed MHV amplitude, just to forget the notation, a particular component amplitude of this, compute it in BCFW, however you'd like, it is a single term. In fact, it is a single Feynman diagram. This particular component of the full super amplitude is a single Feynman diagram, and it is this double box with numerator 1. So it is just a scalar 5-4 theory integral. The problem with this integral is that it has no codimension 8 residues. If you cut all 7 propagators, you get an elliptic integral which has no further residues. And so you get a function of the remaining extra parameter, and there's no special place in that space of that remaining parameter to evaluate a residue. There are no residues. And so it's not possible to fix this coefficient in terms of some codimension 8 that has no codimension 8 residues. So we need something new. Well, the natural coefficient of this box should be this on-shell diagram, clearly. And if you compute this as an on-shell diagram, it depends on one extra degree of freedom, which you can identify by noticing that a corner can be written as a BCFW shift of a pentabox. So this is an ordinary superfunction. It is just an isolated, as a codimension 8 point, a fully ordinary rational function of the external data. And we'd add a BCFW bridge to it, and we get a function that depends on one parameter. Now, what turns out to be the correct solution that I'm going to summarize here in my no minutes remaining is that the correct answer turns out to be really simple. And it took us a long time to find it, and a little while to check it. But it's just amazingly simple. The correct thing is, you include this integral and this function. You normalize this integral so that at anywhere along that extra parameter, so you have this extra parameter with no special isolated points, pick in any point you want and normalize the integral to be 1 at that point. And then evaluate this and write the coefficient so that it matches field theory at that point. Okay, so as long as you match field theory at that point, you're guaranteed to match it there, and this turns out to be the right answer. So let me briefly summarize. So the local integral expression, in a form that's in the paper but not quite in the talk, it basically starts by just listing all of the maximally codimension cuts of the field theory that we want to match. So we write down a list of these cuts, and for each cut, we write down an integral. Forget about the merger. This integral is uniquely determined by the criteria that it has unit residue on this cut. Same with this one and this one. So you just write down the cuts, and for each cut, you tailor a specific integral to match field theory there and nowhere else. And the same thing for the finite integrals. For the finite integrals, we start off, the first term is these double boxes. Instead of doing the double box evaluated at one point, I take a triangle, which is a function of 2 parameters, and evaluate that at any pair, so any point x, y. And then I multiply this by an integral tailored to match field theory at the point x, y, x star, y star. So even though this is a function of 2 variables, just pick any point you want and tailor an integral to match it there. And then you write down the pentaboxes, and you match field theory there, and the double pentagons as well. And this is correct. Again, we've checked it for all end of the KMHV amplitudes up to the end of the 7 and 14 particle, end of the 7 MHV 14 particle amplitude, which required a bit of effort. But anyway, this expression is correct, and it generalizes to higher loops and also for more general theories. Because we have to include these special functions which do not have further isolated cuts, this is exactly what's needed to fix bubble coefficients and triangle coefficients in general quantum field theories at one loop level. So it's kind of nice that these missing ingredient at 2 loops happen to be the extra bit of technology that's required to actually match everything at 1 loop for all theories. Well, that's all the time I have, and so thank you very much.
Okay, I think we have time for a question or two. Well, if not, then let's thank Tim, Marcus, and Jaco again for night. And personally, I'd like to thank them for being so precise with their timing.